Welcome to the Security Maths. The question is, what is the mathematics behind the RSA encryption and decryption scheme? Today we are going to dive deep into this topic. To understand the mathematics, we need to understand two important concepts. The one is modular operation, which we abbreviate as modern, and another one is extended Euclid's algorithm. So, first of all, let's get into the modular operation modern. You can view this as a circle or a clock. So, as in clock, if you are going to measure the time, you will find that there are several hours, and when the minute or the hour end revolves, it will return to the same position after some time. So there is some division and there is some remainder. We will understand it in a little bit. So for our example, let us choose n equal to 10. And then on our this circle or a clock, we just put all of these values, that is 0, 1, 2, and we go on and we put till 9. This is one of the simplest example because our decimal numbers are also made in the same way. So whenever our counting just ends at 9, we put the place 0 and we count from the next one 1, 2, 3, 4, 5, 6, 7, 8, 9. And then again we add 1 to the tens place. So it will be 21. And then we go on and we reach to suppose 99. Then again when we add 1, so we get a hundredths place 100. So the units place is always the remainder when the number is divided by 10. In this operation we will talk about the multiplication modulo operation, and we choose two numbers to operate. First of all, we choose a equal to 7, then we choose b equal to 4, and we compute a multiplied by b, so that is 28. And our operation, as I told you, it is multiplication modulo 10. So as we have got 28 as our answer after multiplication, now we compute the remainder after the division by 10 and we get our answer as 8. Now we will see how the clock resembles to this operation. We have got the answer as 28. Now we rotate this arrow to measure 28 units on this clock. So we see that this clock revolves, it completes one cycle, so it is 10. Then it again completes one cycle and it reaches 20, and then it is 22, and then rotates and it will go to the 28. So on the clock this number is basically 8. This is the modular operation. Now we go to the second one, which is extended Euclid's algorithm. To understand the extended version, we first need to know the basic concepts, which are the Bezos identity, the Euclid's algorithm, and finally we will learn the extended Euclid's algorithm. Let's get into the Bezos identity. Bezos identity says that if we are given two integers a and b whose GCD is 1, then there exist two integers m and n such that ma plus nb it is equal to 1. For example, if the GCD of 2, 3 is equal to 1, we know that the GCD is 1, then we can find like m equal to -1 and n equal to 1, and after this operation like -1 into 2 plus 1 into 3, we get the answer as 1. So these are the values m and n. Now the question arises, are these values of m and n unique? So clearly they are not unique, as we are giving you one more set of values, that is m equal to 2 and n equal to -1. So 2, 2 it is 4, -1, 3 it is -3, 4 minus 3 it is 1. So we got two values of m and n for which ma plus nb equal to 1. Now we get into the Euclid's algorithm. Euclid's algorithm is to compute the GCD of two numbers a and b. And we are not going to discuss whole of the algorithm. For the reference, I have given it on the slide. You can pause and watch it. Now we move to the extended Euclid's algorithm. This algorithm gives us the exact values of m and n in the Bezos identity. For the full algorithm, I refer you to this link. Here we will only see that what this algorithm do. So we see that we get the values of m and n in the Bezos identity. So let us suppose that we are given e and phi n. Those two numbers have GCD 1. Then from the Bezos identity, there exists d and s such that de plus s into phi n equal to 1. So actually it is just ma plus nb equal to 1, but here we are using e and phi n, which are going to be used in the RSA. And now if we do the modulus phi n both side, then the s phi n will go to 0 and the 1 will be as 1 only. So de mod phi n will give us the 1. Till here we have learned the Bezos identity, Euclid's algorithm, and the extended Euclid's algorithm. And overall, we have learned the modulo operation and the extended Euclid's algorithm. Now we see the mechanism of the RSA. So first of all, we choose two big prime numbers p and q and compute their product n equal to pq. So here, for example, we have p equal to 11, q equal to 13. We get n equal to 143. Then we compute phi n, which is the Euler's Totient function p minus 1, q minus 1. So this phi n we get as 120. Then we select E as the encryption key, which has GCD 1 with phi n. So here we see that E is equal to 7. So we are just picking a random number, E equal to 7. Then we find the inverse of E with respect to phi n by the extended Euclidean algorithm that we just learned. And that Euclidean algorithm will give us the value D equal to 103. Now the catch is that it is extremely difficult to find the inverse of E without the knowledge of phi n. So if I am generating these public and private key pairs, so I will not tell the values of these primes p and q. I will only give the value n, and without the knowledge of p and q, the attacker will not be able to calculate the phi n, and if he is unable to calculate the phi n, it is nearly impossible to get the value of inverse of this E as D. Now we see how the RSA works. So let E be the public and D be the private key. So D will be with the receiver and E will be with the sender. And the receiver has sent this E as a public key to the sender. Now the sender selects a message m such that m is less than m, and for here we take m equal to 8. Then he just encrypts m e mod n. So he raises to the power e the message m to the power e modulo n, and gets some number which we call as the ciphertext. So as we have taken here m equal to 8 and e is 7, so we compute 8 to the power 7 modulo 143, and it gives us the result 57. So the ciphertext is 57. Now for the decryption, the message is now being sent to the receiver, and as the private key is only with him, so he has the value D. So what he do? He computes c to the power d mod n and gets the message m back. So in this way, he has decrypted the message. In our example, as the number was 8, so its ciphertext was 57. So we do 57 to the power 103, which is the value of d, modulo 143. Now 57 was actually 8 to the power 7. So the number is 8 to the power 7 times 103 modulo 143. And 7 and 103, they are the numbers such that it is 1 modulo 57. Sorry, 5n. So we get 8 to the power 1 modulo 5n mod 143, which is equal to 8. This is because e into d is congruent to 1 mod 5n. But the question is, why does it happen? I mean, why 8 to the power 1 modulo 5n and we are getting 8 directly? The answer lies in the group theory. This structure forms a group under multiplication, and the order of this group is phi n. So it is just the identity that a to the power order of the group, it is the identity element in a group. Those who have studied group theory, they might relate to this concept. And then if we do 8 to the power phi n plus 1, so 8 to the power phi n, it is identity which is here 1, identity element in the group under multiplication. And so 8 to the power 1 mod phi n, it is basically 8 only. So the answer is in the group theory. All of these concepts like this group theory and the extended Euclidean algorithm, we will cover in our future videos. And now we are giving you some links for the RSA demonstration where you can just choose P and Q numbers, generate the n, phi n, and so on, and you can just encrypt and decrypt the numbers from this. Also, we have made a video where we learn the actual RSA encryption in the Python language. From those videos, you can just encrypt the message between you and your friends also. So let's meet in our future videos.